Very much for the kind invitation to present this piece of work that I've been working on with Matt Dixon, George Davies-Smith, Jared Vandenberg, and Frank Windemeyer, who are all well, at the University of Bristol, with the exception of Matt, who's at the University of Bath. This is a paper that is trying to answer the question of what are the causal effects of education on health and socioeconomic outcomes later in life. This is a question that has been of considerable interest, particularly to economists, but also sociologists and educationalists, to understand whether the differences that we observe in the outcomes between individuals later in life, between those who remain in school for longer and those who leave school at earlier ages, is due to a causal effect of education, or if it reflects some other difference that's perhaps due to confounding or other differences between individuals. The differences that we observe between individuals with high and low levels of education are quite stark and quite large. We don't have a particularly nuanced understanding of what's driving these differences. The key innovation in this paper is that we are exploiting two different natural experiments, two sources of variation, which affect individuals' propensity to remain in school. The first one is one that's been widely used by economists and econometricians for a number of years, and this is a policy reform which has an exogenous effect on the amount of education that individuals receive. So specifically, it forced individuals to remain in school until they were at least age 16. The second source of variation is Mendelian randomization. And this uses genetic variants that we know associate with educational attainment from all of the great work that's being done by the SSGAC. For this paper, we're using the 74 variants that were identified in the OCBE paper in 2016. So these methods have been used quite extensively in literature. So the policy reform has been used quite extensively in econometrics. Mendelian randomization has been used very broadly across statistical genetics and genetic epidemiology. And there have been an increasing number of papers which are using Mendelian randomization to investigate the effects of education. Education and cognition. So I list a couple of papers here from the last couple of years that have used recent findings of genetic variants which associate with education and cognition to have a look at the effects later in life. But what we're really interested in this project is how do the results compare between these two different natural experiments. The literature in econometrics is really quite interesting and is still developing at quite a pace. So going back a few years, there's a paper which exploited policy reforms in the United States and survey data to estimate the effects of education on health. What's really interesting about this paper is that it's a relatively modest sample, and they found some evidence that individuals who are forced to remain in school for longer had lower mortality. This spurred quite a lot of research effort by economists. So again, this is a widely cited paper which uses a mixture of census data and survey data from the United Kingdom, and actually uses the same reform that I'm going to talk about in this project. And what they found was that there was very little evidence of a substantial effect on mortality. And you can see the important features of the reform in this figure. So this is taken straight from Clark and Roy's paper. And I'll see if I can get the mouse to work. There we go. What we are seeing here is the proportion of individuals who left school without a certain level of education. So the reform that we're particularly interested in is this one, which is affected people who were born after September 1957. And the really neat features of the reform are that it had very little effect on individuals' likelihood to go to university. It had relatively little or no detectable effect on individuals' likelihood of remaining in school for 11 or more years. But it had a really quite marked effect on individuals' likelihood of remaining in school for 10 or more years. And you can see a huge drop here, and it's this change and over these dates that we exploit in for the policy reform. And one other really neat feature here is you can see after the reform was implemented, there's a consistent pattern whereby individuals who are born in the summer term still report leaving school at relatively young ages. And this is because the survey question asks them, what age did you leave school? And individuals who were born in the summer were able to leave school when they were younger than 16. And so each of these peaks here relates to individuals born in the summer term. So in this project, we've got two natural experiments. In econometrics and in genetic epidemiology, we refer to these as instrumental variables. The first instrument is the raising of the school leaving age. And this is the policy reform. It was brought into force in September 1972. And one of the really important things to note with this is that the individuals who were affected by this reform were of lower ability. So they're the individuals who would otherwise have left school at age 15. So it's not affecting the population randomly. It's affecting a very specific segment of the population. And it's been quite widely used, and it's considered to be quite a plausible natural experiment, introducing variation into the amount of education that people received. Mendelian randomization, on the other hand, has been much less widely used in econometrics, but has been very widely used in genetic epidemiology. The genetic variants that we're using here are from the discovery sample of the Octave paper, which does not overlap with the sample that we use for the outcomes in this study, all of which were estimated using data from the UK Biobank. We constructed a weighted allele score for educational attainment, harmonizing the alleles between the UK Biobank data and the results reported by Octave. And this allele score, it provides an estimate of the educational attainment of each individual within the sample. There are a number of sources of bias that can affect Mendelian randomization studies. I think it's quite important before getting into further detail of the results just to flag up some of the sources of bias that we're really concerned about. First is weak instrument bias, and this would occur if the genetic variants don't explain or explain only a very small proportion of the variation in educational attainment. We know this isn't really an issue because the Octave study was very carefully conducted, and the SNPs replicate very precisely, as we'll see shortly. The second is pleiotropy. If the genetic variants have direct effects on the outcome but are not mediated via educational attainment, then this can bias the estimates. For example, one thing that we might be very concerned about is cognition. People who have higher IQs are more likely to remain in school, genetic variants which affect cognition and then directly affect some of the outcomes we're interested in, in other words, in ways that are not mediated via educational attainment, those effects could cause bias. Residual population stratification could cause bias. We control for this using principal components, but there may still be residual differences in the population. Assortative mating can induce bias in Mendelian randomization studies if there are associations between the parents of the participants of the UK Biobank. Then this can induce associations between the genetic score for educational attainment and the outcome. And finally, dynastic effects, or as Augustine Kong put it in her recent science paper, the genetics of nurture effects. This is where genetic variants of the parents that associate with educational attainment may have effects on their offspring. Assortative mating and dynastic effects are relatively difficult to control for in this paper because we're using a sample of unrelated individuals, but I'll come on to that in more detail later on. The UK Biobank, I'm fairly confident that most of the people listening to this are going to be very familiar with this study, but briefly, it's a study in the UK that invited 9.2 million people to take part, and these people are all aged between 40 and 70 in about 2008. Of those 9.2 million, just over 500,000 people were consented and went to assessment centres. And during the assessment centre, they had detailed clinical measurements taken, they had biological samples taken for DNA, and a series of clinical measurements. And most importantly, for our purposes, they have genome-wide data on the vast majority of the sample. In this, we restrict ourselves to individuals who are of European ancestry, and we restricted to the unrelated individuals and applied the usual QC metrics as given in the biobank genotype data documentation. So there's more details in the references in the bioRxiv paper that we've published. Just to illustrate the distribution of people, this is a plot which is a simple 2x2 scatter plot of the individual's place of birth. So on the bottom, we've got the east coordinate. On the y-axis, we've got the north coordinate, and it beautifully plots out the a map of the United Kingdom, including showing the population density as you'd expect. One of the nicest features of this is the little plot down here, which is in fact a data error. So we contacted the UK Biobank, and it turns out that all of these individuals have had their birth location divided by 10. So this is a perfect map of the UK, just divided by a factor of 10, which nicely illustrates the importance of plotting your data. So everything that follows, this has been corrected for. This figure just illustrates the natural experiments that we're using and how the exposure that we're looking to identify. So we're interested in the effects of years of education on a range of outcomes in the UK Biobank. We're concerned that the effects of education might suffer from confounding, so that's other things which affect both education and each of these outcomes. We've got two potential each attainment. We define it in two ways. For the policy reform, we define it as whether they remained in school after the age of 15. So this is a binary variable. One of the features of the Biobank questionnaire is that they only ask the age at which people left school to people who said they didn't have a university degree. So we've assumed that people who have college degrees remained in school after the age of 15. For the Mendelian randomization analysis, we've used the definition that the SSGAC proposed in their paper. So this is using the qualifications that people reported having. And it's mapped to 5 levels here. If they report having no qualifications, then they are assumed to leave school at 18. The standard leaving qualifications of CSEs and O-levels are assumed to leave at 16. Individuals with A-levels, which are the final qualification for people leaving school before university, are assumed to be 18, and 20 for vocational training, and 21 for a college degree. We investigated the effects of education on 25 outcomes. This isn't a phenome-wide association study. We've not done a comprehensive assessment of the effects of education on all of the outcomes in Biobank, but we wanted to choose a broad range of outcomes that would be representative of some of the effects that we are pretty confident that education has, such as on income, and some which there is more uncertainty about, such as morbidity and mortality, where the literature is still unresolved about the effects of education. So just quickly, we've got measures of morbidity, and this is from the self-reported data, including whether someone has hypertension, diabetes, stroke, or has experienced depressive episodes. We've got information from cancer registries, which provides evidence about whether they've had a cancer diagnosis. We've got more linked mortality data, which follows participants up for 7 3/4 years. The participants also reported information about their smoking, alcohol, the amount of exercise they did, and their sedentary behavior. We have household, we have 2 indicators of aging, that is grip strength and arterial stiffness. These were both taken during the clinic visit. We have systolic and diastolic blood pressure that was taken using an automatic blood pressure monitor. And we have a relatively crude measure of intelligence, and this is a 0 to 13 item scale that the participants had to answer within 2 minutes. So there were 13 questions that they had to answer during 2 minutes of their visit. They were also asked a question about their subjective well-being. We evaluated the instrumental variable assumptions for both, and these assumptions are threefold. Firstly, that the instruments associate with educational attainment. Secondly, that there are no confounders of the instrument and educational and the outcome. And finally, the exclusion restriction, that the instruments only affect the outcome via their effects on educational attainment. The first assumption we can assess using partial S statistics. The second we can assess but not prove using covariance balance tests. This is a couple of papers in econometrics and epidemiology that have suggested using the observed covariates to provide evidence about the plausibility of those instrumental variable assumptions. So, and finally, the third assumption is much more difficult to test. We can evaluate it using some of the sensitivity analyses in Mendelian randomization, such as MR-EGA for assessing pleiotropism. This is a figure testing the first assumption. It just replicates the figure we saw from the Clark and Royer paper, just using the UK Biobank data. And we see an identical pattern of results, or almost identical, that the reform had very little effect on higher levels of educational attainment, but individuals affected by the reform were much more likely to remain in school to age 16. We estimated the effects of educational attainment on outcomes using 2-stage least squares for the continuous outcomes and additive structural mean models for binary outcomes. This additive structural mean models just estimate risk difference the effects of educational attainment on the risk difference scale. Standard errors are clustered by month, following on from Clark and Royer. And one issue with the UK Biobank data is that it's a highly non-random sample. So it consists of people who were able to attend the study centres, but also they tended to be much more highly educated. So there's a paper by Fry et al. Last year that did a great job of describing the characteristics of the participants. But we account for this using inverse probability weights. And the difference is, you can kind of see on the slide, but from the UK census, which percent of the population left school at age 15, whereas in the UK Biobank, we find that only 17.5% of the population of the sample left school at age 15. So this suggests we've got a very significant undersample of educated individuals. The individuals who were affected by the raising of the school leaving age were about 23 percentage points more likely to remain in school. And each unit increase in the OCBE score is associated with about 1.36 additional years of education. And this is 1.36 rather than 1, because we've tweaked the definition of educational attainment to be more consistent with the UK education system, where people tend to leave university at age 21. And the youngest age that people could really leave school was age 15. This figure just illustrates the concordance between the results reported by OCBE et al. Using the UK Biobank interim release and the results we get an almost 1-for-1 concordance between the coefficients estimated in the two samples. So the results they report replicate very, very nicely. One of the concerns that we've got is that these instruments, these potential instruments, might associate with the covariates, and this could cause bias using covariance balance tests. And the take home from these figures, which you can see in more details in the paper, is that there's some evidence of associations and some evidence of differences by location, particularly for the genetic scores in blue here, but there's not much evidence that they're bigger than the policy reform. We assessed the potential for bias using the genetic scores as well, and again, the plots here look fairly well balanced. Moving on to the results, we found remarkably consistent evidence of effects of schooling across the different outcomes. So first, starting with morbidity, using Mendelian randomization, there was evidence of effects on that a year of education affected hypertension, diabetes, much more modestly stroke, but there's little evidence of effects on depression and cancer. And these were largely consistent between the policy reform and the MR estimates. There was very large and consistent effects on smoking using both approaches, and slightly more heterogeneous effects on income and using the two approaches. Moving on to the indicators of aging, there was very little evidence of an effect on arterial stiffness, but grip strength was, there was some evidence of an effect using both approaches. There's really curious effects on height, which may be driven by assortative mating, and highly consistent evidence of effects on BMI, so more education, BMI. The effects on blood pressure are quite varied, particularly for the policy reform. We've recently published a paper in Nature Human Behavior, which goes into this in more detail, and it looks like there are nonlinear time trends in these variables that could explain these results. There's evidence of effects on cognition for both approaches, and evidence of effects on alcohol, and sedentary behaviour, relatively inconsistent evidence of effects on exercise. So unfortunately, there's not time to go into all the sensitivity analyses that we collect in our archive paper, where we also use MR, EGA, weighted median and mode for the pretty robust. We've looked into whether the weighting makes any difference, and report what's called the reduced form, the association between the instruments and the outcome. These are pretty consistent. One of the interesting findings is the results that change most is the result from height, and suggesting that it could be due to associative mating or some form of confounding. So we were surprised at how consistent the results were between the MR and the rating of the school leaving age. Recall that these natural experiments are focused on very, very different exposures. The policy reform affected individuals who were part of the ability distribution, and then the randomization estimates are shifting everyone across the entire distribution of the results. So you wouldn't necessarily expect them to have the same effect. In conclusion, both approaches suggest that educational attainment does have causal effects on a range of outcomes in later life. For more details, do take a look at the full papers, both on bioRxiv and Nature Human Behaviour. But if anyone has got any questions, please do let me know. There are some references there. But otherwise, thank you very much for listening.